We continue to carry out some exercises, demonstrate some examples in which we make use of the stream function psi and together with the continuity equation. So different pictures, different type of questions to show its different applicability. Now here, earlier we discussed an example where we needed to find the simple thing, just the velocity components and so on. And here we try to find out the stream function for a known velocity field. The velocity field is given to us, and from that we have to find out the stream function. So the example is that we consider a steady two-dimensional incompressible. So it's a two-dimensional flow, no z component, no w there. Then it is incompressible, no variation of mass or density, rho is there, so we don't have to worry about that. And the velocity field, so there is given such that u is equal to ax plus b and v is equal to a minus ay plus cx. So you see that u is dependent on x, while a and b are of course constants, and v is dependent on both y and x. Where a, b, c are constants, the value of constants have been chosen to be half per second, b is 1.5 meter per second, c is 0.35 per second. They want to generate an equation, an expression for stream function, and plot some line. So in this time, we are required to find out what is psi and then plot its graph for certain its values so that we see how the streamlines look like, how the flow field appear to us. Note that the values of constants in the earlier question that we did was given in meters per second. The values of constants in this question is given. A is only something per second, B is meter per second, and C is some constant per second. Why it's being done this way? You will recall that we mentioned and we discussed, we know this, that in any equation, the dimensions should be the same. And therefore, if we need to keep the dimension to be consistent, whatever they are, length in terms of length, breadth, time and so on, then you see that with the constant a, there is a x is multiplying, so the x will have its one dimension, that is length. But b is an absolute constant, so no length there. So keep these things, these units consistent. B has been assigned to be chosen to be 1.5 meters per second. So there is consistency, and what I want to do is to draw your attention to this thing, that remember that the dimension and the unit of the quantities that appear in an equation must be consistent. We look at the question and we try to work out its values. So as before, we know that u is equal to d psi by dy. So here they have written d psi first and then u is on the right hand side and its value is given to us. If I integrate it, I will have some value of psi given to me. So when I integrate, I obtain this value. Since we don't know, we have to write g as some constant of integration. It could have been an absolute constant as we normally write, but in this particular case, we write it just to ensure that everything is consistent. We let the constant depend on g on some variable x, because it may involve the x variable. And if there is no x in g, then when we substitute the values of a, b and other constants, it will automatically reduce to the relevant value. Then we choose the second part, like this u, we take v. V is equal to minus d psi by dx, the partial derivatives, and the values of these then will be equal to, because if this is what we have obtained as psi, then d psi by dx will be this, and if g is the arbitrary constant depending upon x, g prime is only showing that it's a partial derivative with respect to x that is there. When we try to evaluate and equate these integrated equations, we obtain that v should be equal to these two values. They must be identically equal, and therefore it renders that the derivative of g with respect to x should be minus cx, and when we integrate g with respect to x, we will obtain this, where c is some constant of integration, and this time it's a constant, not depending on any other variable. So therefore, we have the value of psi as this. And as before, we can, to be able to draw the streamlines and the plot that the values of streamlines and show it in a graphical form, then we write down as before y is equal to fx form, that y is equal to psi plus all these functions, and for different values of x and b and psi, we should be able to obtain the different values for psi, and plotting them, we obtain this diagram in which the velocity field is shown to us through the streamline in the positive quadrant. Of course, there may be flow on the negative side or in the other three quadrants that exist, but we are only looking for this one and trying to draw. So the plot is drawn for this part. So we have done all the parts. That is, we were required to find out psi from a given velocity field. We determined that psi, and from that psi we were asked to draw the velocity field, the streamlines, and we have drawn here for different values that are given here and shown, and for different values of psi, and you can see that this is the flow field, this is the picture that we see.